Some notes about the expected counts in a chi-squared test. They don't need to be integers, and we do not round them. I usually carry 3 or 4 decimal places as I'm doing my calculations. The row and column totals are the same for the observed table and the expected table, and this is a great way to check your calculation. And for the chi-squared test to be valid, we need at least 1 for the expected count for each cell, and for the average expected count to be greater than or equal to 5. Calculating p-values under the chi-squared distribution. First, know that a chi-squared distribution is a right-skewed distribution. Its values are greater than or equal to 0. So the chi-squared distribution with degrees of freedom equal to 1 is actually the square of a standard normal. So think about that all the negative numbers in the left tail getting squared and sent to the positive values. So, and the minimum one then is going to be 0. The degrees of freedom for the chi-squared when you're doing a contingency table are the number of rows minus 1 times the number of columns minus 1. And the expected value, otherwise known as the population mean of a chi-squared, is its degrees of freedom. So we can see that in this picture. We have some various chi-squared distributions. Degrees of freedom equals 1 comes in sharply from the left there. And the degrees of freedom equals 4 looks like a familiar right-skewed distribution to us. So notice that if we were to locate the balancing point in that distribution, 4 looks reasonable. So the degrees of freedom equals 4. That also means the mean is 4. And degrees of freedom equals 8. You can see that it shifts to the right of it so that its mean is 8. So those are some examples of chi-squared distributions for different degrees of freedom. Now, how do you get the p-value? Well, remember that if you want to think about the chi-squared as the square of a standard normal, in the degrees of freedom equals 1 case, that's what it is, and in larger degrees of freedom, it's just the sum of squared standard normals. But anyway, think about that standard normal and you squaring it. You're kind of sending the left tail and the right tail all together. So the p-value for a not equal to alternative in the chi-squared distribution is just the right tail probability. So you're going to look at the area to the right of your test statistic. Now, if your degrees of freedom are 1, and only if your degrees of freedom are 1, you've got the option of performing a directional alternative. In that case, if the data go in the direction that you thought it should, according to the alternative hypothesis, you just cut that two-sided p-value in half. And otherwise, think about that standard normal distribution. Your test statistic would have been in the wrong tail of the distribution. You would have covered more than half of the distribution. Then your p-value is bigger than a half. All right, so we're not going to deal with, you're not going to see directional alternatives very often in the chi-squared because, again, you're limited only when you have 1 degree of freedom. But if you do, that's how you do it. All right, so back to our example. We want to conduct a chi-squared test at the 5% level to check for a significant difference in the probability of answering yes for pilots and the members of the general public. So our alpha level is 0.05. And we need to state our hypotheses. So the null hypothesis is that the probability of a yes, I'm too close to the bottom of my screen, given that you're a pilot, equals the probability of a yes, given that you're a member of the general public, against our alternative, that those probabilities are not equal. So the probability of yes, given you're a pilot, does not equal the probability of a yes, given that you're a member of the public. All right, so in order to get our test statistic and our p-value, we're going to need to compute our expected counts and our chi-squared statistic. So let's start by getting the column totals. So the number of experienced pilots in our survey, 40 plus 29 is 69, and the number of members of the general public is 61 plus 323, so 384. And the total number of yeses, let's get our row totals now. The total number of yeses is 40 plus 61, so that's 101. And the total number of noes is 29 plus 323, which is 352. Now the total, you can add up your row totals or your column totals. That should all add to the total. It ends up being 453. And you can see that 101 plus 352 equals 453, and the same with 69 plus 384. All right, so now we're ready to go. So step 3 is getting our test statistic, and we still need to get our expected counts. So let's work on this cell first. All right, what's the expected count for each cell in our table? Remember your little mantra, row total times column total divided by total total. So what row is that in? The row total for that row is 101. How about the column that it's in? The column total is 69. And the total total for the table total is 453. So when you take 101 times 69 divided by 453, you get 15.384. All right, how about this cell? Well, the row that it's in, the row total is 101. The column total for the column that it's in is 384. So 101 times 384 divided by 453. Gives us 85.616. And this cell down here has a row total of 352 times a column total of 69 divided by a table total of 453 gives us 53.616. And how about this last cell? It's 352 times 384 divided by 453 gives us 298.384. And now if you take the time and add those 4 expected counts up, you're going to get 453. So I've already checked that calculation, so I think we're good to go. Now we're ready to compute our chi-squared test statistic. And the test statistic is the sum for each cell of the observed minus the expected value squared divided by the expected value. And so that for our table is going to be, our first cell is 40 minus 15.384. Square that, divided by 15.384, plus 61 minus 85.616, squared divided by 85.616, plus 29 minus 53.616, squared divided by 53.616, plus 323 minus 298.384 squared divided by 298.384. And I've got my contributions from each cell, and if I do that in my calculator, I get 59.797. And that is our test statistic. Now, what were we expecting it to be if the null hypothesis were true? What are the degrees of freedom here? There are 2 columns and 2 rows, so 2 minus 1 is 1, and 2 minus 1 is 1, so 1 times 1 is 1. So we were expecting the chi-square test statistic to be 1 if the null hypothesis were true, and it's 60. So that's really, really high. But anyway, let's go ahead and calculate out that p-value. My p-value is going to be the area to the right of the test statistic in the chi-square distribution. So my chi-square distribution is a right-skewed distribution. My test statistic is 59.797. So I need that right tail area as my p-value. All right, so how can I get that? Well, just like we had norm.dist and binom.dist and all those functions in Excel for other distributions, it also has a function for the chi-square distribution. So my p-value is going to be the area to the right of my test statistic. So that's going to be 1 minus chi-square.dist. So CHISQ.dist. And it takes 3 arguments. When you punch this in Excel, you will see. It's going to take our number of interest, so 59.797. The degrees of freedom, which we just computed to be 1, and the cumulative equals true option. And that is going to give you 1.0547 times 10 to the negative 14th. A really teeny tiny p-value. Alright, so now we can make our conclusion about our chi-square test. Alright, so what's our conclusion? Step 5 is comparing our p-value to our alpha. Our p is really, really tiny. It's 1.0547 times 10 to the negative 14th. Our alpha is 0.05. Our p-value is clearly low. So we reject the null hypothesis and conclude there is significant evidence. I'm going to say there's overwhelming evidence with the p being really, really tiny to conclude the probability of a pilot, an experienced pilot, saying whatever it was they said, a pilot, what was it, should not fly at night. Is different than the probability for a member of the general public. Okay, so that's our first example.